40,000 years ago, something changed in Europe. For hundreds of thousands of years, another kind of human had lived across this continent. They survived brutal winters, hunted animals many times their own weight, and endured repeated shifts in climate that transformed entire landscapes. Then, their traces began to disappear. Not after a brief evolutionary experiment. Neanderthals had already survived for roughly 300,000 years. They had endured cold periods severe enough to reshape ecosystems, warmer intervals that pushed forests across former hunting grounds, and generations in which the animals they depended on moved or vanished from entire regions. And still, they survived. Yet by around 40,000 years ago, their long presence across much of Eurasia was fading from the archaeological record. For more than a century, we have tried to explain why. Climate, competition, disease, small populations, Homo sapiens. Each leaves clues. None, by itself, closes the case. Because the deeper we look at Neanderthals, the stranger their disappearance becomes. These were not helpless primitives waiting to be replaced. Their bodies were extraordinarily robust. Their brains were large. They made sophisticated stone tools, controlled fire, hunted dangerous animals at close range, and cared for individuals who survived serious injuries. Everything about them suggests a human population remarkably capable of surviving a world that could kill an unprotected modern person very quickly. And still, they disappeared. So the real question is not simply why Neanderthals died. It is why, after surviving so much for so long, they finally failed to recover. To understand that, we have to return to Ice Age Europe. This was not a continent permanently locked beneath snow. It was a world in motion. Temperatures rose and fell. Forests expanded, retreated, and returned. Open grasslands replaced woodland. Herds shifted across enormous distances as habitats reorganized around them. Neanderthals lived through these changes again and again. Their populations occupied territory stretching from Western Europe deep into Asia. Some regions were abandoned when conditions deteriorated. Others were occupied again when the environment improved. Their world was unstable, but instability itself was nothing new. That creates the first problem with one of the simplest explanations for their extinction. The climate changed. Neanderthals could not adapt. They died. The evidence does not allow the story to remain that simple. Climate had changed before, many times. Whatever finally happened occurred to a population that already had an extraordinary history of surviving environmental disruption. But during their final millennia, another change appeared. A new human population was spreading into Eurasia, Homo sapiens. By roughly 45,000 years ago, modern humans were moving into regions where Neanderthals had lived for immense periods of time. For thousands of years, depending on the region and the dates being considered, the two populations existed within overlapping worlds. Then the Neanderthal archaeological signal faded. The timing immediately makes us suspects. Perhaps Homo sapiens competed for the same prey. Perhaps our populations were larger. Perhaps our social networks extended farther. Perhaps new technologies or behaviors gave us an advantage when resources became scarce. Perhaps violence occurred. But there is no evidence for a single continental war in which modern humans simply exterminated the Neanderthals. And ancient DNA has made that story even harder to defend. Because when these two human populations met, they did not only compete, they also had children together. This was not a clean collision between two species, followed by the destruction of one. Something more complicated happened, and extinction itself may have looked very different from what we imagine. A population does not need an apocalypse to disappear. Imagine scattered groups containing only a small number of people. One loses several experienced hunters. Another experiences a winter with too few surviving children. Prey shifts away from familiar territory. A neighboring group disappears, cutting off potential partners and information. Each event is survivable. Until enough of them happen together, no final battle is required. No single disaster needs to leave a scar in the geological record. A population can simply become smaller, more isolated, and increasingly unable to replace what it loses. That possibility changes the investigation completely. Instead of asking what killed the last Neanderthal, we need to ask what kept Neanderthals alive for so long, and where that survival system could break. How much food did they need? How vulnerable were small groups? How far could knowledge travel between them? And how much margin for error did they really have? The first major clue is preserved in their skeletons: short limbs, a broad trunk, thick, powerful bones, enormous muscular strength. This was a human body extraordinarily well suited to a cold and physically demanding world. But maintaining such a body came at a cost. Every day, even before the hunt began, a Neanderthal had to pay an energy bill very different from ours. And hidden inside the anatomy that helped them survive the Ice Age may be the first clue to why survival eventually became so difficult. If cold alone destroyed the Neanderthals, their skeletons leave us with a problem. Because almost everywhere we look, we find the anatomy of a human remarkably well suited to conserving heat. A Neanderthal standing beside us would not simply look shorter and heavier. The proportions of the body itself were different. The chest was broad and deep. The pelvis was wide. The limbs, especially the lower arms and legs, were relatively short. Beneath the skin was a heavily muscled frame, supported by unusually robust bones. These differences mattered. In extreme cold, the human body is constantly losing heat to the environment. And one of the simplest ways to slow that loss is to reduce the amount of surface exposed relative to the volume producing heat. A compact body helps. Shorter extremities help. A broad torso helps. The same general pattern appears repeatedly among mammals adapted to colder climates. Neanderthals carried it in their skeletons. Even their faces were unusual. Their noses were large and projecting, with an internal nasal anatomy unlike ours. Researchers continue to debate exactly how every feature functioned. But one thing is clear: this was not simply the face of a modern human made heavier. It was the product of a different evolutionary history, and that history had unfolded across Ice Age Eurasia. But surviving cold is not only about preventing heat from escaping. You also have to produce it. Muscle generates heat, and Neanderthals appear to have carried a great deal of muscle. Their arm and leg bones preserve attachment sites shaped by powerful musculature and repeated physical stress. Their bodies were built for a life without machines, vehicles, insulated buildings, or reliable food stores. Every useful calorie had to be found in the landscape, and every calorie had to support an expensive biological machine. Estimates of Neanderthal energy requirements vary depending on body size, climate, activity, and assumptions about metabolism, but many models point in the same direction. A Neanderthal living an active life in a cold environment may have required substantially more energy than many modern humans do today, possibly thousands of calories every day. And during periods of intense activity or severe cold, the requirement could rise even further. That changes how we should look at their powerful bodies. Strength was an advantage, but strength had to be fed. A broad, muscular body could retain heat and generate enormous physical force, but it could not simply shut down when hunting became difficult. The energy bill continued, and there was another expensive organ above it: the Neanderthal brain. On average, Neanderthal cranial capacity was at least comparable to ours, and in many samples, the average is somewhat larger. That does not mean Neanderthals were more intelligent. Brain size alone cannot tell us that, especially when overall body size and brain organization also differ. But large brains are metabolically costly tissue. So now the survival machine begins to look different. A powerful body, a large brain, high physical activity, cold temperatures, all demanding energy from the same landscape. When prey was abundant, that system could work extraordinarily well. A successful hunt could deliver huge quantities of fat and protein. Large herbivores moving across the Pleistocene landscape represented enormous packages of energy, but failure carried a cost. A smaller, less muscular animal can reduce expenditure. A Neanderthal could not redesign his anatomy because a herd moved away, and this may help explain why environmental instability mattered even to humans so well adapted to cold. The danger was not necessarily freezing to death, The danger was the chain reaction that could begin when the ecosystem stopped producing enough energy in the right place at the right time. Imagine a small group during winter. The temperature falls. Energy requirements rise. A familiar herd changes its migration route. Hunters must travel farther. Traveling farther consumes more energy. The hunt fails. Now the same bodies that made these humans formidable predators become increasingly expensive to maintain. Nothing about this requires Neanderthals to be unintelligent or poorly adapted. In fact, the opposite may be true. They were highly adapted, and specialization always comes with conditions. Yet there is an important warning here. We cannot look at Neanderthal anatomy and declare that we have found the cause of their disappearance. They carried these bodies for tens of thousands of generations. If their energy requirements alone were fatal, they should have vanished much earlier. They did not. Something made this biology work. Somehow, Neanderthals repeatedly extracted enough energy from one of the harshest environments inhabited by humans. To understand how, we need evidence that cannot be seen from the shape of a skeleton alone. Fortunately, their bones preserved something else. A chemical signature. Atoms incorporated into their bodies from the food they ate tens of thousands of years ago. And when scientists began reading that signature, they discovered that many Neanderthals occupied a remarkable position in the Ice Age food web, not merely as hunters, but near its very top. Tens of thousands of years after a Neanderthal ate his last meal, traces of that meal can still survive inside his bones. Not pieces of meat, not recognizable plants, atoms. As food moves through an ecosystem, different forms of elements, such as carbon and nitrogen, are incorporated into living tissue. Their isotopic signatures change in measurable ways as energy passes from plants to herbivores, and from herbivores to predators. When scientists measure these signatures in ancient bone collagen, they can estimate where an individual once stood in the food web. And in many Neanderthals, the answer is remarkably high. Their nitrogen isotope values often resemble those expected from top-level carnivores. This does not mean every Neanderthal ate the same diet. They lived across enormous distances and changing environments, and evidence from teeth, sediments, and archaeological sites shows that plants and other foods could also matter. But at many sites, one pattern is difficult to ignore. Large animals were extremely important. Reindeer, horses, bison, wild cattle, and in some places, even mammoths and other massive herbivores. Animal bones found at archaeological sites sometimes preserve cut marks where stone tools sliced through muscle or separated joints. Other marks reveal bones deliberately broken to reach calorie-rich marrow. This was not scavenging alone. Neanderthals were capable hunters, and that makes the scene far more dangerous than the word hunting suggests. There were no rifles, no metal spearheads, no safe distance from which to stop a charging animal. Many Neanderthal weapons appear to have been designed for close-range use. Wooden spears and stone-tipped weapons placed the hunter frighteningly near animals weighing hundreds of kilograms, sometimes much more. A mistake at that distance could crush ribs, break limbs, or kill instantly. Neanderthal skeletons preserve a remarkable number of injuries, although exactly how those injury patterns compare with other prehistoric populations remains debated. What is not difficult to imagine is the physical risk. A large animal does not need to be a predator to kill a human. It only needs mass. And Neanderthals repeatedly entered that dangerous distance because the reward could be enormous. One successful kill could provide meat, fat, marrow, hide, tendons, and bone. For a small group, carrying the high energy demands of powerful bodies through a cold landscape, such a resource could be extraordinarily valuable. This begins to explain how the biological machine we examined earlier could function. Neanderthals were expensive to keep alive, but they lived in landscapes containing enormous concentrations of energy walking on four legs. The strategy worked, until it didn't, because large prey creates a dangerous kind of dependence. Animals migrate. Populations rise and collapse. Vegetation changes. Forests replace open hunting grounds. Climate reorganizes where herds can feed and where humans can find them. And a hunting strategy that performs brilliantly under one set of conditions may become less reliable when the ecosystem shifts. There is another problem. Protein alone is not enough. Humans cannot survive indefinitely by consuming extremely lean meat as their only major energy source. Fat matters enormously, particularly when carbohydrate-rich foods are limited. That means the value of an animal was not simply measured by how much muscle it carried. Season mattered. Body condition mattered. Access to marrow and other energy-rich tissues mattered. A landscape filled with animals could still become nutritionally difficult if those animals were lean, dispersed, or increasingly expensive to catch. Now imagine the calculation facing a Neanderthal group. Their bodies require large amounts of energy. The temperature drops. A herd moves farther away. Hunters must travel farther to find it. That additional travel burns more calories. Then they must approach an animal capable of seriously injuring them. If they succeed, the reward is enormous. If they fail, they return having spent energy they could not afford to lose. And if one experienced hunter is badly injured, the cost does not end with him. A small group has lost part of its hunting capacity. This is where the extinction mystery begins to change shape. Perhaps Neanderthals were not poor survivors. Perhaps they were exceptionally effective survivors, operating a system with very high rewards and very high costs. But there is a danger in pushing that idea too far. Neanderthals were not trapped inside one rigid hunting strategy. Archaeological evidence shows variation across regions and time. Their diets could be flexible. Their prey changed. They exploited different environments. So once again, we have found a vulnerability, but not a cause of extinction. For hundreds of thousands of years, they solved this problem. The question is how. Muscle alone could not do it. Neither could courage. To repeatedly hunt dangerous animals, process carcasses, survive changing landscapes, and teach the next generation where and how to obtain food required something else: planning, knowledge, technology. And when archaeologists began reconstructing the stone fragments Neanderthals left behind, they found evidence of a mind far more sophisticated than the old image of the primitive caveman suggested. Some of their tools were not simply made. They were planned before the first useful edge even existed. For much of modern history, Neanderthal technology seemed to confirm an old assumption. They were primitive. Their archaeological sites contained stone flakes, broken cores, simple points, and cutting edges. Compared with the objects surrounding modern humans thousands of years later, much of it looked crude. But a finished stone tool hides the most important part of its creation, the sequence that came before it. And when archaeologists began reconstructing those sequences, the image of Neanderthal technology changed. One of the clearest examples is a method known as l'évaluation. The principle seems simple: remove a useful flake from a stone core. But the useful flake was often the final step in a much longer process. First, the core had to be prepared. Its surfaces were shaped. Its geometry was controlled. Earlier flakes were removed to create the correct angles and convexities. Only then could the napper strike the core and detach a flake whose general form had already been anticipated. In other words, the desired object had to exist in the mind before it existed in stone. That requires planning. Stone is unforgiving. Strike at the wrong angle, and the fracture travels somewhere else. Use the wrong amount of force, and hours of preparation can be damaged in seconds. There is no way to reverse the mistake. A skilled napper had to understand, through experience, how force would travel through the material. This was not engineering in the modern sense, but it was not random rock breaking either. It was learned technical knowledge. And learned knowledge creates another question. How did a young Neanderthal acquire it? Genes cannot contain instructions for preparing a particular piece of flint. Someone had to demonstrate the process. Someone had to watch. Someone had to practice. And somehow, those techniques had to survive the death of the people who knew them. A recognizable stone tool tradition therefore records more than technology. It records information moving from one generation to another. But stone was only part of the system. Neanderthals also produced composite tools. A sharp stone edge becomes much more useful when attached to a wooden shaft or handle, but joining two different materials creates an engineering problem of its own. The stone must be shaped correctly. The wood must fit. The connection must withstand force. And sometimes, an adhesive helps hold everything together. That brings us to one of the most remarkable materials associated with Neanderthal technology: birch tar. At prehistoric sites in Europe, archaeologists have recovered birch-derived tar associated with Middle Paleolithic technology. Birch bark does not simply provide ready-made glue. It has to be transformed by heat. Exactly how Neanderthals produced tar remains debated, and experiments suggest several methods may have been possible. We should not imagine a prehistoric chemical laboratory, but the important fact remains. Someone discovered that an ordinary natural material could be transformed into something with a completely different function. That discovery had to be recognized, then repeated, then remembered. This is technology in its most fundamental form: knowledge, allowing humans to extract properties from nature that are not immediately obvious. And the archaeological record shows that Neanderthal technology was not identical everywhere. Different regions produced different solutions. Raw materials changed, prey changed, tool forms changed, techniques changed through time. That makes it increasingly difficult to describe Neanderthals as humans trapped inside one rigid behavioral system. They could learn, they could plan, they could modify technology, and they could transmit at least some of that knowledge across generations. So the extinction investigation reaches another dead end. If Neanderthals disappeared simply because they were too primitive to compete, why do their tools reveal this level of planning? The answer may lie not in what a single Neanderthal knew, but in how far that knowledge could travel. Imagine two populations containing equally capable individuals. In the first, groups regularly encounter other groups. Partners move between communities. Materials travel. Ideas spread. If one skilled toolmaker dies, the technique may survive somewhere else in the network. Now imagine the same intelligence distributed across much smaller, more isolated groups. Knowledge has fewer routes through which to survive. If one expert dies, an important technique may disappear locally. If an entire group collapses, generations of accumulated information can disappear with it. Innovation is not only about intelligence. It is also about connectivity. This becomes important when Homo sapiens begins appearing in the same landscapes. Some archaeological records, associated with later modern humans, show materials moving across considerable distances. Stone, pigments, and shells could travel far from their geological sources. That does not prove that every Homo sapiens group possessed a superior network, or that Neanderthals were socially isolated everywhere. The evidence is more complicated, but it raises a possibility. Perhaps the difference was not that one human population could invent and the other could not. Perhaps the difference was the size of the network capable of preserving an invention. For Neanderthals, that distinction could have been critical. Technology needs people. Someone must remember where good stone can be found. Someone must know the movement of animals. Someone must understand fire, wood, plants, and seasons. Someone must teach the next generation. And unlike stone, most of that knowledge leaves almost nothing behind. Wood decays. Fibers disappear. Animal skins decompose. Spoken instructions vanish the moment the voice stops. A stone tool can survive underground for 50,000 years. The knowledge required to make it can disappear in one generation. That is what makes the archaeological record so deceptive. We are seeing only the durable fragments of a much larger survival system, and even those fragments tell us something important. Neanderthals were not technologically helpless. They planned. They learned. They combined materials. They passed knowledge forward. Once again, we have discovered another reason they should have survived. But technology also points towards something stone cannot preserve. A tool requires knowledge. Knowledge requires other people. And the importance of those other people becomes clearest when one member of the group can no longer hunt. Some Neanderthal skeletons preserved devastating injuries. Broken bones healed. Damaged bodies survived. Individuals who should have become costly to keep alive remained alive long after the initial injury. In a world where every calorie mattered, that should not have been easy. Which means the next clue is not preserved in a tool. It is preserved in the bodies of the people their groups refused to leave behind. A broken stone tool can be replaced. A broken hunter is a different problem. For a small Neanderthal group, every adult mattered. Hunting required strength. Moving across difficult terrain required endurance. Food had to be found, carried, and processed. An individual who could no longer perform those tasks consumed resources without contributing in the same way. In a world where calories were expensive, that should have been dangerous. Yet some Neanderthal skeletons show that seriously impaired individuals did not simply die when they became unable to function normally. They survived. One of the most famous examples comes from Shanidar Cave, in what is now northern Iraq. Known as Shanidar I, this Neanderthal male lived with an extraordinary collection of injuries. His right arm was severely damaged and may have been largely unusable. The lower portion of the limb was missing. He suffered damage around the face and eye, and other skeletal problems affected his movement. Whatever the precise sequence of injuries, this was not the body of a fully capable hunter. And yet he did not die immediately. The bones show extensive healing. He survived long enough for his body to adapt to injuries that would have made everyday life far more difficult. That creates a forensic problem. How? A severely impaired person in the Pleistocene could not buy food, remain safely at home, or rely on stored supplies delivered by strangers. If the group moved, he had to move with them, or somehow survive without them. If food was shared, someone else had to acquire it. If an injury required protection while healing, other members of the group had to tolerate the cost. Shanidar I is not the only clue. Other Neanderthal remains preserve healed fractures, severe tooth loss, and degenerative conditions that individuals survived for significant periods. This does not prove that Neanderthals practiced medicine in the modern sense. A healed bone is not evidence of a doctor. And we should be careful not to turn every injury into proof of organized healthcare. But the evidence does allow a more restrained conclusion. Some Neanderthals survived conditions that would have reduced their ability to obtain food or protect themselves independently. That strongly suggests social support mattered. Someone stayed. Someone shared resources. Someone allowed an injured individual time to heal. And this changes the old image of Neanderthal life. For decades, their robust skeletons and dangerous hunting strategies encouraged a picture of humans surviving almost entirely through physical strength. But strength alone cannot explain a disabled individual living for years. Cooperation can. In fact, cooperation may have been one of the most important survival technologies Neanderthals possessed. A successful hunter could feed more than himself. An experienced older individual could retain knowledge even after physical ability declined. Someone unable to hunt might still process food, maintain tools, tend fire, teach younger members, or remember landscapes visited decades earlier. We cannot reconstruct the daily role of a specific injured Neanderthal from bone alone. But this is precisely why survival, after severe impairment, matters. It reveals that the value of an individual was not necessarily measured only by immediate physical productivity. That has enormous implications for the extinction mystery, because a population capable of supporting vulnerable members was not simply a collection of isolated hunters, it was a social system. And social systems can absorb shocks. If one hunter is injured, others compensate. If a child loses a parent, food can still be shared. If an older individual can no longer chase prey, knowledge may remain inside the group. Cooperation creates resilience, but only up to a point. Imagine a group of 20 people. One injured hunter can be supported, perhaps two. But what happens after several adults disappear? What happens when births fall? What happens when neighboring groups become too distant to replace lost partners? The same social structure that protects individuals cannot create new people from nothing. And this is where the evidence begins, moving away from individual skeletons towards something much larger: population size. For most of their existence, Neanderthals were spread across an enormous territory. But enormous territory does not necessarily mean enormous population. A map can be deceptive. If small groups are scattered across thousands of kilometers, two communities shown close together on a continental map may still be separated by days or weeks of travel. That distance matters. People are not interchangeable units. A small group needs enough adults of different ages. It needs potential partners. It needs children who survive. It needs knowledge distributed across more than one person. And occasionally, it needs contact with people outside the group. Without that contact, isolation begins to accumulate consequences. This is something bones alone can only hint at. But ancient DNA can see it much more clearly. Seen inside a Neanderthal genome is a record not just of one individual, but of ancestry. Population size leaves patterns. Isolation leaves patterns. Related parents leave patterns. And when researchers began sequencing Neanderthal DNA, they discovered something potentially more dangerous than any mammoth or Ice Age winter. Some Neanderthal populations appear to have been very small. In some cases, extremely small. That does not mean every Neanderthal lived in an isolated family at the edge of extinction. Their population history was complex, and different groups experienced different levels of contact. But the genetic evidence increasingly points toward a world of relatively sparse, fragmented populations. Suddenly, the injuries we have been examining take on another meaning. A healed fracture proves resilience at the level of the individual. But every injured hunter also reminds us how much could depend on a very small number of people. The Neanderthals may have possessed something deeply human, the willingness to keep vulnerable members alive. Yet compassion could not solve every demographic problem. You can share food with an injured hunter. You can protect a child. You can carry knowledge through another winter. But if a group becomes too small, there comes a point when cooperation is no longer enough. And buried inside Neanderthal DNA is evidence that some groups may have been moving dangerously close to that point. A population does not need to be weak to disappear. It only needs to become too small. For most of their history, Neanderthals occupied an enormous geographic range, stretching across Europe and into Western and Central Asia. On a map, that looks like success. But geography can hide something important. There may never have been very many Neanderthals at any one time. Ancient DNA has transformed our ability to investigate this problem. A genome does more than identify an individual. It contains traces of the population that individual came from, how closely related its ancestors were, how much genetic diversity existed, and how populations separated or reconnected through time. And the picture emerging from Neanderthal DNA is not one of a vast, densely connected humanity. It is a picture of relatively small populations, often separated across enormous landscapes. Some genetic studies suggest long-term effective population sizes far below those associated with later expanding Homo sapiens populations. Effective population size is not the same as simply counting every living Neanderthal. It is a genetic measure influenced by how many individuals actually contributed offspring to later generations. But the implication is still important. Neanderthal populations were often demographically fragile. One extraordinary genome makes that fragility almost uncomfortably personal. A Neanderthal woman, whose remains were discovered in the Altai Mountains of Siberia, had parents who were closely related. Genetic analysis suggested a relationship comparable to very close relatives. That does not mean all Neanderthals routinely reproduced with close family members. Other genomes show different histories, but it demonstrates what can happen when human groups become small and isolated. Potential partners become scarce, and isolation leaves fingerprints in DNA. At another Neanderthal site, genetic evidence has allowed researchers to reconstruct relationships among individuals who lived within the same community. The result gives us something archaeology rarely provides: a glimpse of an actual Neanderthal social group. These were not abstract dots on a migration map. They were fathers, daughters, relatives, and other individuals sharing the same landscape. And the genetic patterns suggest that at least some communities may have been remarkably small. Now the extinction problem changes. Imagine a population of millions. A hunting accident is tragic. A severe winter is costly. A local group disappearing is almost invisible at the scale of the species. Now imagine the same events occurring across a sparse network of tiny communities. The mathematics becomes unforgiving. Suppose a group loses several adults during a difficult decade. Perhaps hunting becomes less reliable. Perhaps fewer children survive. Perhaps neighboring communities move away or disappear. The group does not need to be wiped out. It only needs to fall below the point where normal fluctuations become difficult to absorb. This is demographic stochasticity. Chance events becoming dangerous because the population experiencing them is small. A slight imbalance between males and females can matter. Several unsuccessful births can matter. The death of a few reproductive adults can matter. Events that would barely affect a large population can reshape the future of a small one. Then comes the second problem, fragmentation. A small population can remain viable if it is connected to others. People move between groups. Partners arrive. Genes move. Knowledge moves. A community that loses members can sometimes recover through contact with neighboring communities. But as groups become more isolated, those rescue routes begin to disappear. And environmental change can make the distances between communities effectively larger. A river changes. A forest expands. A prey population moves. A familiar corridor becomes less productive. Two groups that once encountered each other may stop meeting. Nothing dramatic has happened, but a connection has been broken. This may be one reason climate instability mattered, even though Neanderthals had survived climate change before. The question is not simply whether an individual Neanderthal could survive cold. Clearly they could. The question is what repeated environmental disruption did to the network connecting small populations across the landscape. A local population could disappear and later be replaced if other groups remained nearby. But if several neighboring populations declined at the same time, recolonization became harder. Empty territory could stay empty. The network could begin to contract, and once that process started, it could reinforce itself. Fewer people meant fewer potential partners. Fewer partners meant less genetic exchange. Smaller groups became more vulnerable to chance losses. Local extinctions removed connections from the network, and every missing connection made the remaining groups more isolated. No catastrophe is required, only pressure, repeated long enough. This gives us a very different image of extinction. There may never have been a morning when thousands of Neanderthals suddenly died. There may have been no final battlefield, no single winter that killed them all. Instead, imagine lights disappearing from a map. One community vanishes, then another. A region once occupied becomes empty. Far away, other groups continue hunting, making tools, raising children, and living ordinary Neanderthal lives. They may have had no idea that their entire population was shrinking. From inside the process, extinction might not have looked like extinction at all. It might simply have looked like fewer encounters. Longer distances, missing relatives, hunting territories where nobody returned. And yet this explanation has a problem of its own. Neanderthals had probably lived in relatively small populations for a very long time. Small population size did not suddenly appear 40,000 years ago. Once again, we have identified vulnerability, not the trigger. Something still has to explain why a demographic system that had persisted for so long finally failed. And during the period when Neanderthal populations were approaching their final disappearance, another demographic system was expanding into the same world. Homo sapiens. They arrived with bodies less specialized for extreme cold. They were not necessarily stronger. Their brains were not dramatically larger. And they entered landscapes Neanderthals had understood for thousands of generations. If survival were simply a contest of physical adaptation, the newcomers should not have had an obvious advantage. But populations compete differently from individuals. A group does not need stronger hunters if it can replace losses faster. It does not need every individual to know more if information can travel farther. It does not need to defeat another population in battle if it gradually occupies the spaces that population can no longer refill. Around the same time that the Neanderthal network was becoming increasingly vulnerable, the archaeological record begins showing Homo sapiens across more of Eurasia. Two human populations were now occupying overlapping worlds. One had survived there for hundreds of thousands of years. The other had only recently arrived. And within several thousand years, only one would remain recognizable as a distinct human population. That timing is impossible to ignore, but it does not tell us what happened. To understand that, we have to reconstruct one of the most consequential encounters in human history. Not the moment one species met another, the moment two different human populations began sharing the same world. Around 45,000 years ago, the human landscape of Europe began to change. Neanderthals were no longer alone. Homo sapiens had expanded out of Africa and were moving through Eurasia. Eventually, modern humans reached territories where Neanderthals had lived for thousands of generations. For the first time, two different human populations occupied parts of the same world. The timing is difficult to ignore. Not long after Homo sapiens appeared across more of Europe, Neanderthals disappeared as a distinct population. For decades, this coincidence encouraged a simple story. We arrived. We were smarter. We defeated them. But the evidence does not give us anything that clean. There is no archaeological layer stretching across Europe that records a single war of extermination. No continent-wide battlefield. No clear wave of Neanderthal bodies killed by modern human weapons. Violence between individuals or groups may have occurred. Two populations using some of the same landscapes and resources could certainly come into conflict. But possible violence is very different from demonstrating genocide. If Homo sapiens contributed to Neanderthal disappearance, the mechanism may have been much quieter. Consider population size. A Neanderthal group might contain only a small number of individuals and depend heavily on contact with neighboring groups. Now imagine new communities entering the same landscape. They do not need to attack anyone. They only need food, water, shelter, stone, wood, access to migration routes. The same things Neanderthals needed. Competition can happen without a battle. If two populations hunt the same herd, the group that reaches it first changes the prospects of the other. If one occupies a productive valley, another may have to travel farther. If one population can maintain more people across the landscape, every local loss becomes easier for it to replace. This is where the comparison becomes interesting. Physically, Neanderthals possessed obvious advantages in some environments. They were robust, powerful, cold-adapted. They knew Eurasian landscapes that their ancestors had inhabited for immense periods of time. Homo sapiens did not arrive as an obviously superior biological machine. Our advantage, if there was one, may have existed at another scale. Networks. Archaeological sites associated with early modern humans contain evidence that some materials traveled considerable distances. Stone moved away from geological sources. Shells appeared far inland. Pigments and ornaments circulated through human communities. None of these objects alone proves that Homo sapiens had universally larger or better social networks than Neanderthals. And the archaeological record varies greatly between regions. But taken together, they raise a possibility with enormous consequences. A human group connected to distant groups has access to more than distant objects. It has access to people, potential partners, information, alternative territories, techniques developed elsewhere, and perhaps support when local conditions fail. Imagine two communities facing the same ecological crisis. A herd disappears. The first community knows only the surrounding territory and a few neighboring groups. The second is connected, directly or indirectly, to people far beyond the local landscape. Neither group needs to be more intelligent, but one may have more options. That difference becomes especially powerful over generations. Innovation is fragile. One person discovers a better way to shape a point. Another learns a new hunting technique. Someone remembers a water source beyond the usual territory. If knowledge remains inside a tiny group, an accident can erase it. If knowledge moves across a wider network, it can survive the death of the person who first carried it. Population size and information begin reinforcing each other. More connections preserve more knowledge. More knowledge can help more people survive. More survivors maintain more connections. If Neanderthal groups were generally smaller and more fragmented, they may have faced the opposite feedback. But we have to be careful. This is not proof that Homo sapiens arrived with a single revolutionary advantage and immediately displaced everyone else. The overlap lasted long enough for interaction to become complicated. Different technologies appeared in different places. Cultural traditions changed. Neanderthal groups may themselves have adopted or developed new behaviors during this period. The boundary between the two populations was not a clean line moving across a map. And then genetics destroyed the simplest version of the story entirely. When scientists began comparing ancient Neanderthal genomes with the genomes of living humans, they found sequences that should not have been there if the two populations had remained completely separate. For many people alive today, especially those with ancestry outside sub-Saharan Africa, a small portion of the genome can be traced to Neanderthal ancestors. The implication is unavoidable. Homo sapiens and Neanderthals did not merely see one another from opposite sides of a valley. At some point, members of these populations met closely enough to reproduce. Their descendants survived, and eventually, some of those descendants became ancestors of people alive today. That changes the investigation, because now the arrival of Homo sapiens cannot be described only as competition. It was also contact, exchange, and interbreeding. The distinction matters enormously. Imagine a small population living beside a much larger one. Even if nobody is killed, repeated interbreeding can gradually change the smaller population. Children carry ancestry from both groups. Those children reproduce. Over generations, genetic boundaries become less distinct. If one population is much larger, ancestry from the smaller population can be absorbed into the expanding one, while the smaller population loses its identity as a separate demographic group. This does not mean interbreeding alone explains Neanderthal disappearance. It almost certainly does not. Nor does Neanderthal DNA in modern humans mean that Neanderthals never became extinct as a distinct population. They did. Their recognizable populations, anatomy, and archaeological presence disappeared. But extinction was no longer a simple story of one humanity dying while another watched. Some of the people on both sides became part of the same family tree, and that raises a disturbing possibility. For more than a century, researchers searched for evidence of what Homo sapiens did to Neanderthals. Perhaps the more important question is, what happened when the boundary between them began to dissolve? Competition could reduce Neanderthal numbers. Climate instability could fragment communities. Small populations could make every loss more dangerous. And interbreeding could move some Neanderthal ancestry into a population that was expanding, while theirs was shrinking. None of these processes requires a final battle. Together, they could produce something much harder to see archaeologically, a disappearance without a single moment of destruction. And we know that at least one part of this process happened, because the evidence is not buried only in caves. It is inside living people. For tens of thousands of years, the last physical traces of Neanderthals lay underground. Then we learned how to read their DNA, and what emerged from those genomes would force us to reconsider what the word extinction actually means. For most of modern history, the disappearance of the Neanderthals seemed complete. Their bones remained, their tools remained, but the people themselves were gone. Then scientists recovered something far more revealing from ancient bone: DNA. Extracting genetic material from remains tens of thousands of years old is extraordinarily difficult. After death, DNA begins breaking into smaller fragments. Heat, moisture, and microorganisms accelerate the destruction. Modern human contamination can overwhelm the tiny amount of ancient material that survives. But under the right conditions, fragments remain, and those fragments change the case. In 2010, researchers published a draft Neanderthal genome assembled from ancient remains. For the first time, scientists could compare Neanderthal DNA directly with the genomes of living humans. If Neanderthals and Homo sapiens had remained completely separate after our lineages diverged, the genetic pattern should have reflected that separation. It did not. Many living people with ancestry outside Africa carry a small percentage of DNA inherited from Neanderthals, commonly around 1 to 2% in an individual genome, although ancestry patterns vary between populations. 1 or 2% sounds insignificant. It is not, because those fragments are not identical in every person. One individual may carry Neanderthal-derived sequences in one region of the genome, while another carries different fragments elsewhere. Across living populations, the surviving pieces collectively preserve far more of Neanderthal genetic variation than any single person carries. The implication is unavoidable. At some point after Homo sapiens expanded out of Africa, members of our population encountered Neanderthals and reproduced with them. Their children survived. Some had children of their own, and their descendants carried Neanderthal DNA forward for tens of thousands of years. This was not speculation based on similar bones or tools. It was ancestry, written into the genome. But the discovery created a strange paradox. Neanderthals disappeared as a distinct population, yet part of their ancestry survived inside the population that remained. So what exactly happened when the two groups met? Genetics gives us clues. Neanderthal-derived variants found in modern humans have been associated with aspects of immune function, skin biology, metabolism, and other biological processes. Some may have been useful as Homo sapiens entered environments our ancestors had not occupied for long. Neanderthals had lived in Eurasia for immense periods of time. Their populations had already encountered local pathogens, climates, and ecological pressures. Interbreeding offered Homo sapiens something evolution normally acquires very slowly, existing adaptations from another human population. But this inheritance came with a filter. Not every Neanderthal sequence survived equally well. Over thousands of generations, natural selection removed many Neanderthal-derived variants from modern human populations, while others persisted. The genome we carry today is therefore not a preserved Neanderthal genome hidden inside us. It is a scattered archive. Fragments that survived reproduction, chance, and selection. And those fragments reveal something important about extinction. Imagine a small Neanderthal population living near a much larger population of Homo sapiens. If individuals occasionally reproduce across the boundary, children carry ancestry from both. Some descendants remain among Neanderthal communities. Others become part of expanding Homo sapiens populations. Now repeat that process across generations. If the Neanderthal population is already shrinking, while the Homo sapiens population is expanding, gene flow does not affect both sides equally. An individual moving from a group of thousands into a group of millions barely changes the larger population. But movement in the opposite direction can matter enormously to the smaller one. Over time, the demographic boundary can weaken. This is sometimes described as assimilation. It offers a very different picture from conquest. No army is required. No final massacre. No moment when the last Neanderthal has to understand that an entire human population is ending. Instead, some lineages simply continue inside another population. But we should not push the evidence beyond what it can tell us. Interbreeding occurred. That is established. Interbreeding contributed Neanderthal ancestry to later Homo sapiens. That is established too. But whether assimilation was a major cause of Neanderthal disappearance, and how important it was, compared with climate, demography, or competition, remains debated. The genetic evidence does not give us permission to replace one simple extinction story with another. Instead, it adds another suspect, and it makes the case more complicated. Because extinction usually creates an intuitive image. A population exists, then something kills its members. Eventually, none remain. But human populations can disappear in another way. Their numbers can fall. Their communities can fragment. Their distinctive traditions can vanish. And their surviving members can become incorporated into other populations. At the end of that process, the original population no longer exists as a recognizable group. Yet some of its ancestry remains. This may be part of what happened to the Neanderthals, and it explains why saying they never went extinct would also be misleading. They did disappear. There are no Neanderthal communities today. No population maintains a continuous Neanderthal identity. Their characteristic anatomy vanished from the human landscape. Their archaeological traditions ended. What survived was something smaller, fragments. A piece of DNA inherited here, another there. Tiny genetic records carried by descendants who would eventually have no idea where those sequences came from. For tens of thousands of years, that inheritance remained invisible. Then ancient genomics allowed us to recognize it. And suddenly, the Neanderthal extinction was no longer a story involving only the dead. Part of the evidence was walking around in the living. But DNA does not solve the mystery. It makes the final reconstruction possible. We now have a population adapted to extreme environments. a body with high energy demands, a dependence on complex hunting and learned technology, evidence of cooperation, small and sometimes fragmented populations, rapid environmental instability, an expanding Homo sapiens population entering the same landscapes, and direct evidence that the two populations interbred. Each clue explains part of the disappearance. None explains all of it. The question is no longer which single suspect killed the Neanderthals. The question is, what happens when all of these pressures arrive at the same time? To answer that, we have to return to the final thousands of years and place every piece of evidence on the same timeline. Only then can we reconstruct how a human population that survived for hundreds of thousands of years finally disappeared. By now, the investigation has produced too many suspects: climate, energy, population size, isolation, competition, interbreeding. The temptation is to choose one, but the evidence points towards something more complicated. To understand the final disappearance of the Neanderthals, we have to stop looking for a single killer and reconstruct the system that was beginning to fail. Start with climate. The final millennia of Neanderthal existence unfolded during a period of substantial climatic instability. Temperatures could change rapidly, vegetation shifted, animal communities reorganized. Neanderthals had survived environmental change before. That is precisely why climate alone is not enough. But climate does not need to kill people directly to become dangerous. Move the prey, and hunters must travel farther. Change vegetation, and familiar hunting grounds become less productive. Fragment suitable habitat, and neighboring human groups become harder to reach. For a large population, these disruptions may be temporary. For a sparse population, they can become demographic damage. Now add the Neanderthal body: powerful, cold-adapted, physically expensive. High energy demands meant that unreliable access to food could create pressure quickly. Again, this was not a fatal flaw. Neanderthals had supported these bodies for thousands of generations, but when hunting became less predictable, the margin between energy gained and energy spent could narrow. Then add population size. This may be where the separate clues begin to connect. A small group loses two experienced adults. Under normal conditions, neighboring groups might eventually replace that loss through migration or new partnerships. But what if neighboring groups are also shrinking? What if environmental changes have increased the distance between them? What if contact that once happened every few years now happens rarely? A temporary loss becomes permanent. The network weakens. Then Homo sapiens enters the landscape. This does not require an invasion. Imagine instead that modern human groups simply occupy some of the same productive environments. They hunt some of the same animals. They use some of the same raw materials. They need water, shelter, and territory. Even without direct violence, another human population changes the ecological equation. And if Homo sapiens populations were larger or more connected in some regions, the imbalance could grow over generations. A Neanderthal group disappears from a valley. A modern human group occupies it. The Neanderthal population nearby loses a potential connection. Homo sapiens gains another. One network contracts while another expands. No single event looks like extinction, but the map slowly changes. Now add interbreeding. We know it happened. Some encounters between the two populations produced descendants whose genetic legacy survived. For a shrinking population, that creates another possible route toward disappearance. Some Neanderthal individuals may have entered Homo sapiens communities. Some descendants of mixed ancestry may have become increasingly incorporated into the expanding population. Their genes continued. Their population identity did not. This is why asking what killed the Neanderthals may be the wrong forensic question. Perhaps there was no single mechanism. Imagine instead a series of pressures acting together. Climate makes prey less predictable. Higher travel costs strain energy budgets. Small communities lose members. Isolation reduces opportunities for recovery. Homo sapiens occupies overlapping territory. Competition adds pressure. Interbreeding transfers some ancestry into the expanding population. Each factor alone is survivable. Together, they can create a feedback loop. Fewer Neanderthals means fewer connections. Fewer connections mean less demographic resilience. Lower resilience makes environmental shocks more dangerous. Local extinctions increase isolation. Greater isolation makes future local extinctions more likely. Eventually, the system reaches a point where recovery becomes increasingly difficult. And this model explains something a dramatic extinction story cannot. Why we do not find a single moment when the Neanderthals ended. Their disappearance was not simultaneous everywhere. Different populations vanished at different times. Some regions may have been abandoned before others. Some groups may have persisted longer. Dating the final sites is difficult, and claims for exceptionally late survival remain debated. The edge of extinction is blurry. That is exactly what we might expect if we are looking at demographic collapse rather than a single catastrophe. But there is still something we cannot reconstruct. We do not know the identity of the last Neanderthal. There was no witness recording the moment, no final inscription, no grave marked as the end of a human population. And whoever belonged to those final generations probably did not know they were living at the end of anything. They woke. They searched for food. They repaired tools. They cared for children. They watched seasons change. Perhaps they occasionally encountered people who looked different, spoke differently, or carried unfamiliar objects. Perhaps some of those strangers became competitors. Perhaps some became partners. Life continued, until the archaeological signal did not. That may be the most unsettling part of the entire case. Extinction does not have to feel like extinction to the people experiencing it. From inside a collapsing population, the world may simply become emptier. A neighboring group stops appearing. A familiar camp is abandoned. There are fewer partners, fewer children, longer journeys between people. Then one generation becomes the last without ever knowing it. We can now answer part of the question that began this investigation. Neanderthals probably did not disappear because they suddenly became incapable of surviving the Ice Age. They were not simply too stupid. They were not technologically helpless. And there is no evidence for a single event in which Homo sapiens exterminated them across Eurasia. The evidence instead points toward interacting pressures acting on populations that may already have had little demographic margin for error. But disappearance still hides one final problem. Because some members of those populations left descendants. Their DNA crossed the boundary. Their ancestry entered ours. So somewhere between the last recognizably Neanderthal communities and the expanding populations of Homo sapiens, the distinction that had existed for hundreds of thousands of years finally dissolved. We can reconstruct many of the pressures. We can see the demographic vulnerability. We can detect the interbreeding. But we cannot identify the exact moment when one humanity ended and another remained. Which leaves us with the final piece of the case. Not what killed the last Neanderthal, but whether the last Neanderthal is even the right way to think about what happened. Somewhere in Eurasia, tens of thousands of years ago, a Neanderthal was born into one of the final generations of their people. We do not know where. We do not know whether that individual understood that neighboring groups were disappearing. And we almost certainly will never know who the last Neanderthal was. There may not even have been a clean moment when such a person could have been identified. Because populations do not always end with a final survivor standing alone. Sometimes, their boundaries simply dissolve. For hundreds of thousands of years, Neanderthals had survived a world of extraordinary instability. They endured severe cold. They adapted to changing landscapes. They hunted dangerous animals at close range. They learned complex methods of shaping stone. They transformed natural materials into useful technology. They supported individuals who survived serious injuries, and they passed enough knowledge from generation to generation for that survival system to persist across immense spans of time. Nothing in that record looks like a population waiting helplessly for extinction. Yet eventually, the system stopped recovering. The evidence we have examined suggests why there may never be a single answer. Climate mattered, but Neanderthals had survived climate change before. Their high energy demands mattered, but those bodies had supported them for thousands of generations. Small population size mattered, but small populations had persisted for a very long time. Homo sapiens mattered, but there is no evidence of a single extermination event across Eurasia. Interbreeding mattered, but it cannot explain every disappearance in every region. The mystery becomes clearer only when these clues are allowed to interact. A small population does not need much additional pressure before ordinary problems become dangerous. Environmental instability can move prey. Moving prey increases the cost of hunting. Failed hunts matter more when there are fewer hunters. Losing people makes small groups more isolated. Isolation reduces access to partners, knowledge, and support from neighboring communities. Then another human population enters the same landscape. It does not need to destroy every Neanderthal group. It only needs to change an already fragile equation. Some Neanderthal communities disappear. Some may move. Some encounter Homo sapiens. And some of those encounters produce children. Generation after generation, the map changes. Eventually, the archaeological record no longer contains populations we can clearly identify as Neanderthal. Their distinctive human presence ends. For more than a century, that looked like the end of the story. Then, in the 21st century, scientists began reconstructing the Neanderthal genome. Ancient bones were cleaned under controlled conditions. Tiny fragments of damaged DNA were extracted. Sequences were assembled, and those sequences were compared with the genomes of living humans. The result connected two worlds separated by roughly 40,000 years. Neanderthal DNA was still here, not an intact Neanderthal genome hidden inside modern people. Not proof that Neanderthals somehow survived unchanged. Fragments. Different fragments in different individuals. Pieces of ancestry scattered across living populations. The last Neanderthal communities were gone, but some Neanderthal lineages had crossed into ours before that happened. That distinction changes the meaning of the case. Biologically, Neanderthals did disappear as a distinct population. There are no Neanderthal communities alive today. Their characteristic anatomy no longer exists as a separate human form. Their cultural traditions cannot be followed continuously into the present. Calling them simply still alive would erase what was genuinely lost. But calling their disappearance total would miss something equally important. Some of their descendants survived. That means the final chapter of Neanderthal history may not have been a scene of complete replacement. It may have included absorption. The boundary between them and us was crossed before one side disappeared. And perhaps this is why the old question feels increasingly inadequate. For generations, we asked why Homo sapiens won and Neanderthals lost. It is an understandable question. Only one of those names exists as a living population today. But evolution does not recognize winners and losers in the way human stories do. It preserves whatever continues reproducing. A population can vanish while some of its genes survive. A culture can disappear while descendants remain. A human group can cease to exist as a distinct identity without every lineage ending. The Neanderthal story contains all of these possibilities. And there is still much we do not know. We do not know the exact weight climate carried, compared with competition. We do not know how often encounters between the two populations were peaceful or violent. We do not know how frequently individuals moved from one population into the other. We do not know whether the final decline felt sudden across a few generations or almost invisible across many. Archaeology gives us fragments. Genetics gives us fragments. Geology gives us fragments. The reconstruction between them will probably never be complete, but the evidence allows one conclusion. Neanderthals did not disappear because they were simply incapable of survival. Their existence proves the opposite. For hundreds of thousands of years, they survived environments that repeatedly changed around them. What eventually disappeared was not an inferior human suddenly defeated by a superior one. It was a population caught inside a changing system. Small numbers, environmental pressure, isolation, another expanding humanity, and contact between the two. Some groups vanished. Some lineages ended. Others crossed over. And 40,000 years later, we can still detect them, not in a hidden valley, not frozen intact beneath the ice, not as another species waiting to be discovered, but in sequences of DNA carried by living humans. So perhaps the most important question was never why the Neanderthals lost. They survived cold, injury, hunger, and enormous environmental change for hundreds of thousands of years. Eventually, their populations disappeared, but some of their descendants did not. They are alive now, not as Neanderthals, as part of us. And that leaves one question the archaeological record may never be able to answer completely. When one human population disappears into another, where exactly does extinction end?